All right, let's dive into this explainer and completely demystify the mathematical arena that makes all of quantum mechanics possible. If you've been studying physics, you know that setting up a problem usually means defining the space where your particle actually lives. But when we zoom way down into the quantum realm, the standard mathematical tools we use to describe, say, a ball flying through the air, they simply stop working. To describe a quantum state, we need a totally different mathematical architecture. We need the Hilbert space.
So you might be wondering, why does the classical 3D space of our everyday reality simply break down when describing a quantum particle? Well, think about it. In classical mechanics, you can describe exactly where a particle is and how fast it's moving, using your standard coordinates x, y, and z. We call this a real space because naturally the coordinates are defined by real numbers. But in quantum mechanics, a particle isn't just sitting at one specific point. It exists in a fluid state of probability, often expressed as a linear combination of many possible states at once. Our standard 3D geometry, it literally just doesn't have the capacity to handle the abstract, probabilistic nature of these wave functions.
So here is our roadmap for this explainer. First, we'll look at familiar vectors in 2D space, then stretching to infinite dimensions, the need for completeness, the generalized inner product, defining the Hilbert space, and finally, normalizing quantum wave functions.
Let's jump right into part 1, familiar vectors in 2D space.
Okay, let's anchor ourselves in something super familiar to build up some immediate confidence: standard Euclidean geometry. Think about a normal 2D or 3D graph. You've got basis vectors, like the familiar I, j, and k unit vectors. Any physical vector, like velocity, is really just a linear combination of those base states, scaling them up or down with real numbers. Now, quantum space actually uses the exact same foundational logic, but it scales it way, way up. Instead of physical arrows pointing in space, we use abstract state vectors, or kets. Instead of the real numbers we use for classical coordinates, our quantum constants belong to complex numbers to represent probability amplitudes. And instead of just 2 or 3 basis vectors, a quantum system can actually require an infinite number of basis states to form its coordinates.
Which perfectly leads us into part 2, stretching to infinite dimensions.
Now here's where things get really fascinating. Quantum systems frequently require combinations of infinite basis states. When a particle's position is totally undefined, it can theoretically be in a superposition of infinitely many outcome states. But when we stretch standard linear algebra to infinity, we hit a massive mathematical mystery where infinite sums can yield total nonsense. You see, in a finite vector space, if you add 2 vectors together, you always get another vector that safely lives inside that exact same space. But infinity is a concept, not a number. When you take the limit to infinity, your resulting vector can suddenly just pop right out of existence from your original mathematical space. And obviously, if our quantum state falls out of our vector space, it's suddenly no longer a quantum state.
Think of it kind of like a sequence of rational numbers converging to the irrational number pi. Without strict boundaries, our mathematical limits can literally fall right out of the space. To visualize this, imagine a vector space made entirely of finite polynomial functions. You take x, you add x squared, add x cubed, and so on. You're adding polynomials together, so you should definitely get another polynomial, right? Well, actually, no. If you carefully choose your coefficients and stretch that linear combination all the way out to infinity, you actually form the Taylor series for e to the x. The exponential function e to the x is completely outside the polynomial vector space. It's honestly as absurd as adding an infinite pile of rocks together and suddenly getting an apple pie. It just doesn't make sense.
So how do we fix this? That brings us to part 3, the need for completeness.
To solve this geometric breakdown, we need a mathematical patch to trap these infinite sums so they don't fall off the geometric edge. We have to establish a hard rule that guarantees our quantum states will actually remain quantum states, no matter how many infinite superpositions are at play. Enter Cauchy completeness. This property basically gives our space no gaps, turning abstract set theory into a strict visual boundary. If you have a sequence of vectors converging toward a limit, Cauchy completeness acts as an unbreakable mathematical wall. It forces that final limit to exist strictly inside your vector space. The space is complete. It includes its own edges. By requiring our quantum vector space to be Cauchy complete, we absolutely guarantee that an infinite sum of valid basis kets will always result in another valid physical quantum state. No apple pies here.
Moving right along to part 4, the generalized inner product.
All right, so we need a second patch for our mathematical arena, one that maintains the geometry, the angles, and the distances that we rely on in finite geometry, so we can actually make physical measurements. By taking the familiar dot product and generalizing it, we can project abstract quantum vectors onto one another to find distinct physical probabilities. Think back to classical geometry. The dot product tells us how much one vector overlaps with another. It's essentially projecting a shadow of one vector onto another. Well, in our quantum space, this generalized dot product is called the inner product. If you have an initial state vector and you want to know the exact chance it collapses into a specific final state when you measure it, you just take the inner product of the two. The inner product spits out a complex scalar number, which represents the probability amplitude of that specific outcome. It's literally the ultimate bridge between abstract math and physical observation.
Let's pull it all together in Part 5, Defining the Hilbert Space.
Okay, we finally have all the puzzle pieces to answer David Hilbert's legendary question. What actually is this space? It's pretty straightforward, really. A Hilbert space is simply a linear vector space defined over complex numbers, equipped with an inner product to handle generalized lengths and probabilities, and strictly Cauchy-complete to ensure infinite sequences never fall out of bounds. That's it. That's the whole shebang. That is the true arena of quantum mechanics. It allows us to safely use the awesome power of linear algebra to manipulate state vectors, knowing for absolutely sure that the mathematics will perfectly reflect the discrete physical realities of the quantum universe.
Finally, let's look at Part 6, Normalizing Quantum Wave Functions.
Let's bring all this abstract math back down to something highly tangible. How do we make absolutely sure our wave functions behave correctly inside this Hilbert space? Well, just as a classical 2D unit vector has a length of 1, a normalized quantum wave function must represent a total physical probability of exactly 1. Remember, in a classical physical space, if we want to talk purely about direction without worrying about length, we scale our vector down to a unit vector of length 1. In a Hilbert space, the length of our state vector translates directly to the total probability of finding our particle anywhere in the universe. Since the particle must definitely exist somewhere, the sum of all probability outcomes must equal exactly 1. Not 0.9, not 1.1, exactly 1.
So let's walk through this normalization calculation methodically so you can see exactly how to scale a quantum state down to a unit vector. Suppose your state is a linear combination of two basis states. State 1 has a coefficient of 1, and state 2 has a complex coefficient of 2i. To find the total probability, we take the modulus square of those amplitudes. The modulus square of 1 is just 1 squared, which is 1. The modulus square of the complex number 2i is 4. Add them together, 1 plus 4 equals 5. But wait, our total probability is currently 5, not 1. So this state vector is not normalized. To fix this, it's super easy. We simply divide the entire wave function by the square root of that sum, which is 1 over the square root of 5. Multiplying our state by this normalization constant shrinks our quantum vector perfectly down to a length of 1, ensuring our physical probabilities are mathematically sound. Boom, done.
And there you have it. We've built a solid bridge from classical geometry straight to quantum completeness, leaving you with the perfect mathematical framework to explore the quantum universe. By ensuring our space has no infinite gaps and properly tracks physical probability amplitudes, the Hilbert space gives us the ultimate foundation to unravel the mysteries of atomic spins, molecular bonds, and wild superpositions. So, armed with your complete mathematical map, I leave you with this to ponder. What unknown quantum systems are you going to explore next?